So this problem deals with decimal number palindrome check. So the problem statement is given a decimal number, return true if it is a palindrome and false if it is not. So we know that we're going to consider all negative numbers as not a palindrome, so that should be a trivial check. So we give a couple of examples. So the number 434 is going to return true because the last digit and the first digit and the last digit are the same. And if it is even, then this will give you true if there's 4 digits, right? So the last and the first are the same, and second and third are the same. What is not a palindrome, for example, 431 should return false because first and the last digits are not the same thing. So as we can see that if we have an even number of digits, we're going to do n divided by 2 number of comparisons, and otherwise we're going to ignore the digit in the middle. So if it is a odd number, then I'm not going to consider the number in the middle, and if other numbers work out, then this number is considered a palindrome. Alright, so in the solution we're going to use modulo, and we're going to use some kind of masking. So the core problem we're dealing with in this problem is, first we have to figure out how many times the loop is going to iterate over, because obviously we're going to compare the first and last digit, and we're going to compare digit by digit. This means that we're running a loop the number of times, whatever number of times, the same as how many digits or how many single place digits are in the number. So if this number is in the thousands, then we're going to run the loop 2 times. So because there's 4 digits, so we're comparing the first and last digit each time, and so we can cut the digit in 2. Okay, so first we have to figure out how many digits there are in a given number. This number could be, a billion, and it's going to be, I believe 10 digits. And how do we figure that out? Right, so we could just use a simple tool in math. We just use the logarithm operator. This is also present in Python here. So the log base 10 would give you roughly how many digits there are. So in order to make it concrete, we're going to log 10 on the number, and we're going to floor it, and we're going to add it by 1. So this is how many digits there would be in the number. So what this means is that, for example, if we have 100, so log base 10 of 100 will give you 2, because 10 to the second power is going to be 100. So similarly, if we have 1,000, then something in the thousands, then it's going to be between 3. So log 10 of n, where n is in the thousands area. This is going to give you somewhere in 3 to 4, but not including 4, because if this gives you 4, then that means we have 10,000, right? So then we have to, because we are running the loop an integer number of times, we have to either round it down, round it up. So in this case, we always round down and then we add 1, because see, in the 100 case, we are this is gonna give you a 2, but 100 actually has 3 decimal places, 3 digits in it. So we have to do it 3 times, not 2 times. So the similar with in the thousands case, we always do it 4 times, not 3 times. So we always run it down to 3, and then we add 1 to give us 4. So this solves our problem with of how many times the loop is going to run. And the next problem we're going to deal with is we have to compare the least and most significant figures. And how are we going to do that? So in the previous problem, we figured out we could use modulo 10 to extract out the least significant figure, which is to the rightmost in a decimal number. And this time we're going to extract out the most significant bit, and that we're going to use integer division. So we give an example. So say we have 2,300 and we want to extract out the 2, then we have to divide by 1,000. If we divide by 1,000, this will give us 2.3. And then we could only take the integer part, which we could do with the double division, which is this in Python. So this just truncates the number, and it's not going to round. It's just going to take the whatever is to the left of the decimal place. So in this case, it's going to be 2. So if 2,300 divided integer division by 1,000 will give you just 2, and it's gonna get rid of that 3. So this is the way we're going to use it to extract out the most significant bit. Figure. Okay, so let's see an implementation of the code. So obviously the edge case is if the number is a negative number, then we're just going to return 0. We're going to return false. And then this line essentially is this operation here. So this tells us how many iterations we're going to go through in the loop. And the most significant digit masking is this operation here, which we're going to raise 10 to the some power, and this is going to use in the integer division here to extract out the most significant bit. And here we're going to take the least significant bit, we're going to compare them. If they're not the same, we're going to return false. Then if they are the same, then we're going to keep checking, right? So the next digit we're going to check, we're going to get rid of the least significant bit, and we're going to get rid of the most significant bit. So this is how we get rid of the most significant bit, and this is how we get rid of, you guys can remember this from the last video, that we take out the least significant bit with this operation, and this would get rid of the most significant bit. So this will give us, for example, 2,300 modulo by 1,000. This would give us 300, right? So this gets rid of the most significant bit. This always gets rid of the most significant bit. So we're left with this. We are extracting out the least significant bit, and we're extracting out the most significant bit. So after this operation, this number is going to become 30 if we have this, and we're going to check 30 next. And of course, since we're going to use the this kind of masking every time in a loop, we have to modify this mask too in order for us to use it and not cause any error. So since the number of digits decrease in the number we're going to check, whether it is a palindrome, we also have to shrink the size of the mask. So since we are getting rid of two number places in every iteration, we have to get rid of 2 places in the mask too. So that's why we divide by 1,000, divided by 100 because 100 has 2 zeros in it, so we kind of get rid of 2 zeros. And we could continue this operation and until, if we don't encounter this, if we don't encounter a situation where the least significant and most significant figures don't matching, and then we conclude that it is a palindrome, we can return true. So in this case, then the runtime is going to be big O of log of n because of this operation here, which defines how many times we're going to run the loop. Okay, so just to reiterate, we are first extracting out the first and the last bit, and then we're comparing them. This is what we do here with these lines of code. And then we're going to get rid of the most significant bit and get rid of the least significant bit, these two operations here. And then we're going to modify the mask and we're going to iterate over the loop again. So if you will, this acts kind of like a pointer if you're comparing two strings. And this acts just as extracting out the string, the character in the string, and comparing them. So if you follow this example and work out a couple examples of actual input, then you'll probably see that you'll figure out like this way of extracting out digits and of doing the masking, use modular operation would be very applicable to many situations where you might encounter in the future.